Given this observation, it's now straightforward to show a reduction from the independent set problem to the clique problem. Now we're doing a reduction from independent set to clique, so we have to take an input for the independent set problem and transform it to an input for the clique problem. So consider an input for the independent set problem. This is defined by a graph G and a goal little g. We take the opposite of G, that's G bar, and we use G bar and the same little g as our input to the clique problem. Now we use our observation. If we get a set S, which is a clique in the opposite graph G bar, then we know that S is an independent set in the original graph G. Now if we get a solution S for the clique problem, that means that S is a clique of size at least little g in G bar. Then we return S as a solution to the independent set problem, because we know S is an independent set of size at least little g in the original graph capital G. Now if our clique problem returns no, so there's no clique of size at least little g in G bar, then we return no for the independent set problem, because we know that there's no independent set of size at least little g in the original graph G. Because if there was an independent set of sufficient size in capital G, then we know there would be a clique of sufficient size in the opposite graph G bar. This completes the definition of the reduction, and the proof of correctness follows from this observation. Therefore, we've shown that the clique problem is NP-complete.